I'm just going to demonstrate how to carry out a simple cable calculation using the tables from BS 7671. As you can see, put a question on the board and I'll read it. It says a circuit is wired in flat twin and earth 70-degree thermoplastic cable. That's the normal flat twin and earth cable that we would use in house wiring, say. The circuit's going to be 23 metres long and it's to supply a load of 7 kilowatts. Cables to be run in a roof void, laid on top of 100mm of thermal insulation. The roof void will reach temperatures of 38 degrees. Circuit protection is going to be a BSEN 60898 Type B protective device. So what we need to do really is we need to calculate the size of the cable. So if we start off right at the very beginning, the first thing we need to do is find out what sort of current a 7 kilowatt load is going to take. So very simple calculation. The very first step is to calculate the design current. And for design current, we use the symbol IB. That stands for design current. If we divide the power by the voltage, that will give us current. So our load is going to be 7 kilowatts, which is 7,000 watts. If I divide it by 230 volts, I end up with a current which is going to be flowing in the cable of 30.43 amps. That's our design current. And I now need to find a protective device which is suitable for it. Now clearly, a protective device would need to be either equal to or greater than that current, because if I choose a protective device less, the protective device will be overloaded. I know that the nearest rating protective device in a BSEN 60898 circuit breaker would be 32 amps. The symbol we use for our protective device is IN. So now we've got IB as our design current, IN is our protective device rating. I now need to look at the question and find any environmental influences which are going to affect the cable, such as temperature, the way it's been installed, and they're what we call rating factors. And for the rating factors, first of all, I need to identify what they are, and then I need to refer back to BS 7671 to find out what the values I need to use for those rating factors. So looking at the question, we can see that it's going to be laid on top of 100mm of thermal insulation. We can take that into account when we look at our installation methods, because it's just laying on top. We'll get to that in a moment, but that would just be an installation method really. The one thing that we need to be concerned about is the temperature. Okay, so we now need to look in BS 7671 at our rating table for ambient temperature, and like I say, our ambient temperature is 38 degrees. If we look at the table 4B1, we can see that it goes up in increments of 5 degrees. Now, obviously it goes 30, 35, 40. Because it's 38, it's no good me installing it at 35 degrees, so I need to take a value which is higher, but as close to as possible. And I look in the table, 4B1, BS 7671, and you can see that for a 70-degree cable, I have a factor of 0.87. Once we've found our rating factor, or factors, because often there's more than one that would affect the cable, we need to divide the rating factor into IN so that we can decide on the size of the cable that we need to use. The reason the rating factors are in place is to ensure that whenever a cable is installed, no matter what the environmental influences are, it doesn't rise above 70 degrees when it's under full load. That's the main problem with installing cables. We need to keep them cool. And as we can see, 70 degrees is the maximum. Because it's in a temperature of 38 degrees, the cable's going to start off hotter than it would normally. Most of our cables, if we look at the table in BS 7671, are calculated at 30 degrees. So if we've installed in a cable at 30 degrees ambient temperature, the factor's 1. So we know that if we divide or multiply anything by 1, we're going to end up with the same value. So 30 degrees is the norm. Anything above that, we need to calculate for. And it's going to make us choose a bigger cable, because when current flows through a cable, the cable warms up. It's just a natural occurrence. So for me, I've got my rating factor of 0.87. I've divided it into my protective device rating, and I've come up with a value of 36.78 amps. All that's doing is telling me that I need to find a cable now which can carry 36.78 amps under the installed condition of being in a roof void on top of 100 millimetres of thermal insulation. To find the correct installation method, I need to refer back to BS 7671. Because it's flat twin and earth and there's insulation involved, I have to use table 4A2. We can see that from table 4A2, the closest reference method I could get to is method 100. Next, we have to go to table 4D5, because that gives us our current rating for flat twin cable. Once we get to table 4D5, we can use this reference method to help us decide on what size cable we should use. If we refer to table 4D5, we can see that using method 100, the nearest rating cable I can get to 36.78 amps, which is above it. It could be equal to or above, but for our case it's going to have to be above it. The nearest cable I can get is 45 amps, and that would mean I have to use a 10 millimetre squared cable. The next step for us now, having decided on the rating of the cable and the size of the cable we're going to use, is to check that the cable comes inside the volt drop constraints that we're allowed. And we know that for a lighting circuit we're allowed 3%, and for a power circuit we're allowed 5%. 5% of 230 volts is 11.5 volts, so we need just to check. So using our table again, 4D5, if we look to the right-hand side, we'll see that our cable that we're going to install, a 10mm cable, has a volt drop of 4.4 millivolts per amp per metre. Okay, when we say per amp, we mean the amount of current which is actually going to flow in the cable. So for our case, we use 30.43, that's the amount of current that our load is going to use. It's 23 metres long, we can see up there, 23 metres long, and it's 4.4 millivolts per amp per metre. That's this calculation. Because this value is in millivolts, we need to convert it to volts, so we just divide the whole of the top line by 1,000, and that will convert to volts for us. And if we do the calculation, we can see that we've got a value of 3.07 volts, which is well inside 11.5 volts, just as we would expect it to be, because of course we're using a 10mm cable. Okay, having decided on the size of the cable we're going to use, the next step is to make sure that in the event of a fault, the protective device will operate very, very quickly. In this case, because it's a BSEN 60898, it needs to operate on fault currents within 0.1 of a second. So first thing I need to identify really is the type of system. If we say that this cable is going to be installed on a TNS system, without measuring it, we know that a TNS system is going to have a maximum ZE of 0.8. You'll find that information in the on-site guide. So we'll use that value. We need to do a calculation to find the maximum earth loop impedance of our circuit, which we call ZS. And we know that ZS is equal to ZE, which is 0.8, plus R1 and R2 of the cable. Now R1 is the term we give to the resistance for our line conductor, and R2 is the term we give for the resistance of our CPC. If we look at table L1 in our on-site guide, it gives us all of the different resistance values for any combination of cables up to about 25 mil. So we now need to look at table L1 in the on-site guide and find the resistance of R1 and R2 per metre, and from that we can then calculate the complete resistance of our cable. So if we look in table L1 of the on-site guide, we can see that a 10 mil line conductor with a 4 mil CPC is going to have a resistance of 6.44 milliohms per metre. So we'll show that in the calculation as little r1 and little r2, times the length, because it is per metre, and divide it by 1,000, and that will give us r1 and r2 for the whole length of that cable. We call that big R1 and big R2. Do the calculation, and I can see that my cable has a resistance of 0.148. Now, the next step really is for us to calculate for temperature. As we've seen earlier, our cable can operate at 70 degrees. If we look at table L1, we can see that the resistances of our cables are made and measured at 20 degrees. So this value would be the resistance of our cable per metre when it was at 20 degrees. We know that it could possibly get to 70 degrees. We have to take that into account. The resistance of our copper that we use will rise by 2% for every 5 degrees rise in temperature. So if our cable starts off at 20 degrees and it goes up to 70 degrees, it's going to rise 50 degrees. So if it raises 50 degrees in temperature, that means that the resistance is going to increase by 20%. We don't really need to remember all of that because we can look at a table in the on-site guide again, which will actually tell us. The table we need to use is table L3. And if we look at the bottom left-hand corner of that, it tells us that where our CPC is bunched with other cables, we need to use a factor of 1.2. Now we know if we multiply anything by 1.2, we increase it by 20%. So I need to multiply my 0.148 by 1.2, and that will give me the actual value that cable resistance would be if it was ever to reach 70 degrees. If I multiply the resistance of the cable by 1.2 to take into account the rise in temperature, I end up now with a value of 0.177 ohms. And as we can see, this value would be my R1 and R2. All I need to do now is add it to ZE, and that will give me the ZS, the actual ZS of the circuit. We can see that ZS equals ZE plus R1 plus R2. We know that ZE is 0.8 because it's given to us here. We've calculated the resistance of our cable as being 0.177, and that would be at its maximum temperature of 70 degrees. So if we add the two together, we end up with a ZS of 0.977. All I need to do now is compare that to the value given to me in BS 7671 on our tables for protective devices, and this needs to be lower. The table we need to use is table 41.3, and from that table we can see that we're allowed a maximum permissible value for a 32 amp type B circuit breaker of 1.44 ohms. Providing this value is less than that, then this circuit would be satisfactory. I'm just going to demonstrate how to carry out a simple cable calculation using the very beginning. The first thing we need to do is find out what sort of current a 7 kilowatt load is going to take. So, very simple calculation. The very first step is to calculate the design current. And for design current, we use the symbol IB. That stands for design current. If we divide the power by the voltage, that will give us tables from BS7671. As you can see, put a question on the board and I'll read it. It says a circuit is wired in flat twin and earth 70-degree thermoplastic cable. That's the normal flat twin and earth cable that we would use in house wiring, say. The circuit's going to be 23 metres long and it's to supply a load of 7 kilowatts. Cables to be run in a roof void, laid on top of 100mm of thermal insulation. The roof void will reach temperatures of 38 degrees. Circuit protection is going to be a BSEN 60898 Type B protective device. So what we need to do really is we need to calculate the size of the cable. So if we start off right at this current, so our load is going to be 7 kilowatts, which is 7,000 watts. If I divide it by 230 volts, I end up with a current which is going to be flowing in the cable of 30.43 amps. That's our design current. And I now need to find a protective device which is suitable for it. Now clearly, a protective device would need